Hello students, welcome back to another video of calculus. Today we will discuss the sequential criteria for limits. Sequential criteria for limits. In the previous chapter we have seen the sequence. Now in this chapter we will see the sequential criteria for limits. Sequential criteria for limits. So, first of all, we know that the sequence of real number converges to some real number in the previous chapter. Now, we will see one theorem that will be the sequential criteria. So, the statement of the theorem is, let f from a to r means real valued function, a to r, and let small c be the cluster point of a, be the cluster point means all the elements of A are very close to C, be the cluster point of A, then the following statements are equivalent, then the following are equivalent. Following are equivalent. First statement is, limit x tends to c, f of x is equals to L, limit x tends to c, f of x is equals to L, and the second statement means is, for every sequence, suppose xn, for every sequence xn in A, that is a sequence in domain, for every sequence xn in A that converges to C, every sequence in A such that converges to C, that converges to cluster point of A C, such that xn is not equals to C for all n belongs to set of natural numbers, means this xn is not a constant sequence. then the sequence f of xn, then the sequence of f of xn means sequence of images of this xn. Xn is sequence in this A and f of xn will be the elements of this R. So, f of xn means image of this xn under this f in R. So, f of xn is the sequence in codomain. If the sequence in domain converges to C, then f of xn, that is the sequence in codomain, must converge to this L, that is this converges to L, These two statements are equivalent, means if this limit exists, then this condition holds, that is every sequence which converges to C in domain, the image of that sequence converges to this limit in codomain, and if the second statement holds, that is every sequence which is converges to C in domain, then if their image converges to limit L, that is f of xn converges to L, then limit of f of x is equals to L, that is limit of that function f of x is equals to L. This is the statement. So, we have to prove that these statements are equivalent, that is 1 implies 2 and 2 implies 1. So, in this proof, the first part is, so proof of the theorem. Proof of this theorem. So, first part will, in the first part we will prove 1 implies 2, and in the second part we will prove 2 implies 1. So, part 1 is to prove 1 implies 2, that is if we suppose first statement, then the second statement holds, and in the second part we will prove second suppose, and the first part is proved. So, we will assume that the limit x tends to C, f of x is equals to L, that is the limit exists. So, assume that limit x tends to C, f of x is equals to L. limit x tends to c, f of x is equals to L. Then we have to prove that if xn is sequence that converges to c, which is not constant sequence, then we have to prove that the image of that sequence, that is f of xn, converges to L. So, let xn be a sequence in A such that xn converges to c. So, let this xn be a sequence, xn be a sequence in domain A such that xn converges to C. Our claim is the image of this sequence, that is f of xn, converges to this limit L. Our claim is to show that for epsilon positive, that is we can use the definition, epsilon delta definition of convergence of sequence. For epsilon positive, there exists some, suppose n naught belongs to set of natural number, because n is already taken in this here. So, n naught belongs to set of natural numbers such that mod of this limit exists, means that is the sequence converges to L, means mod of f of x minus L is less than epsilon, mod of f of xn minus L is less than epsilon for all n greater than or equals to n naught. This is the definition of limit of a sequence that we have seen in the second chapter. So, here this is our claim, but we have assumed this limit x tends to c, f of x is equals to c. If this limit exists, again we can use the epsilon L definition, epsilon delta definition on limit, that is in this chapter we have seen in previous videos the limit of a function. So, we can use that definition, since the limit x tends to c, f of x is equals to L. Therefore, for given epsilon positive, there exists some delta positive such that for x belongs to A, 0 less than mod x minus c less than delta implies mod of f of x minus L less than epsilon. This is the definition of limit. As this sequence xn converges to C, so again by definition of convergence of sequence we can write, since the sequence xn converges to C, therefore there exists another n naught belongs to set of natural numbers such that by definition of convergence of sequence we can write mod of this xn minus c less than some delta, mod of xn minus c is less than some delta for all n greater than or equals to n naught, for all n greater equal n naught. This is by definition of convergence of sequence. Therefore, here we have this 0 less than mod x is x minus c less than delta implies f of x minus L is less than epsilon. Again this xn converges to x, so we can use the definition of convergence. Now, from these two equations, suppose this is equation number 1, this is equation number 2. Therefore, from this equation we can write mod of f of x n minus L for 0 less than x less than c, for 0 less than mod x minus c less than delta, we have mod of f of x minus L less than epsilon, and here we have this mod of xn minus c less than delta for all n greater equal n naught. So, using these two, here again epsilon greater than 0 there exists delta positive, again here there exists some delta for which xn minus c less than. So, if we replace xn here instead of x, if we write xn, then we can use these two equations. Therefore, equation 1 can be written as, so by using equation 1 we can write Therefore, from equation 1 we have mod of f of xn minus L is less than epsilon whenever n greater equal n naught. Just replacing x by xn in that equation we can write this. Therefore, if our xn converges to C, then this f of xn converges to L. By definition of convergence of sequence implies f of xn converges to L. Hence, the proof of first part. Now, the second part. Now, the part second. In the part second, we have to suppose the second statement and prove the first one. So, to prove second implies first. So, assume that xn is sequence in A which converges to C, also their image, that is f of xn converges to L. Therefore, we have to prove limit x tends to C, f of x is equals to L. So, assume that sequence xn is sequence in A, such that xn converges to C implies f of xn converges to L. If xn converges to C, then their image, that is f of xn, converges to L. Now, we have to prove that limit x tends to C, f of x is equals to L. This is our claim. Our claim is limit x tends to C, f of x is equals to L. Now, we will suppose contrary, that limit x tends to C, f of x is not equals to L, then we will get some contradiction. So, on contrary, suppose that this limit is different. On contrary, suppose limit x tends to C, f of x is not equals to L. F of x, limit x tends to C, f of x not equals to 1. Therefore, there exists some epsilon greater than 0. Suppose epsilon not greater than 0, such that for every delta positive, there exists at least one element of A. There exists at least one, suppose x delta, we will say that x delta belongs to A. This is the element of A, we will just use that notation x delta, such that if 0 less than mod, that x delta minus C less than delta implies mod of f of x, suppose delta, f of x delta minus L is either greater than or equals to epsilon naught. This limit does not exist means this condition is not satisfied. So, that is for there is some element in A for which the image of that element is not close to L. This is the the contrary definition to existence of limit. Therefore, for all n belongs to set of natural numbers there exist some, suppose some radius, or we can write suppose some xn belongs to set A. For every n there exists some xn belongs to A with mod of xn minus C is less than 1 by n, for which mod xn minus C less than n, that is for this is the condition for the limit, first condition, mod of xn minus C less than 1 upon n. Therefore, the sequence xn converges to C, but the f of xn does not converges to L. This is by using definition of convergence of sequence. This is contradiction. Mod of xn minus C less than some epsilon, but this mod of f of that xn minus L is greater than or equals to epsilon naught. So, this is contradiction to the that sequence f of xn converges to L, but xn converges to C, but f of xn does not converge to L, does not converge to L, because mod of xn minus C less than some epsilon, but mod of that f of xn, here instead of delta we can use the xn. So f of xn minus L is greater or equal epsilon means this f of xn, there exists some elements of A for which the image of that element is not close to L, but that elements are very close to C. So this is the contradiction to given assumption. So this is contradiction to our hypothesis, which is contradiction, hence the limit of that sequence, hence the limit of f of x must be L, hence the proof of this theorem, that is these two statements are equivalent. Now we will see some divergence criteria whenever our function is divergent. So the next topic is divergence criteria. Divergence criteria. So suppose the sequence xn, suppose this xn is sequence in domain, is sequence in, suppose domain A is sequence in A such that xn is not a constant sequence, also that xn converges to C, that is one sequence which is converges to C, then the first statement is f of xn, if the image of that xn, that is f of xn does not converge, f of xn does not converge, then limit x tends to C, f of x does not exist, f of x does not exist. That is, if we find a sequence in domain A which converges to cluster point of A, but the image of that sequence does not convergent, that is the image of convergent sequence in domain is not convergent in domain codomain, then we limit of given function does not exist. Now the second condition is, that is the second criteria is, if f of xn, that is the image of xn does not converge to given limit, given real number L, then either limit x tends to C, f of x does not exist, limit x tends to C, f of x does not exist, or limit x tends to C, f of x exists but not equals to L, exist, or limit x tends to C, f of x exists but that limit x tends to C, f of x is not equals to L. So there are two possibilities. If the image of xn does not converge to given limit L, then there are two possibilities, either that limit does not exist or that limit exists but not equals to L. Now the third criteria is, third statement is, if yn is any another sequence, if yn is another sequence, if yn is any another sequence in domain A, such that yn is not equals to C and which converges to C, that is any another sequence in domain which converges to C, that on which same point xn converges. So yn is any another sequence in A such that yn converges to C, and the sequence f of xn and f of yn, that is the images of both sequences xn and yn converges to different points, that is if the xn and yn are two sequences in domain which converges to same point in domain, but their images f of xn and f of yn converges to different limits, that is different points in codomain, different points, then again the limit f of x, limit of f of x does not exist, limit x tends to c, f of x does not exist. These are some sequential criteria, divergence criteria for the given limit. Now we can use these criteria to check whether the given sequence is convergent or divergent. The examples on this theorem and this divergent criteria we will see in the next video.